Welcome back to Life and Biology. I'm Dr. Joel Graff. This will be the last condensed lecture dealing with the basics of chemistry and organic chemistry. So again, we'll start with looking at the periodic table of elements. And what we are talking about today is elements and how they react with one another. The first thing to point out is that these elements over here in the 18th group of the periodic table are non-reactive. They have a full set of electrons in their outer orbital, so that means they are don't have any real need to interact with anyone else because of this. So when it comes to talking about how these other elements are going to be forming chemical reactions, forming bonds, chemical bonds, one of the most important properties to consider is one called electronegativity. Now the periodic table is set up in rows and columns, and we even have some color coding on this particular periodic table, and the color coding is giving us a hint as to which elements behave similarly to each other. And there is a trend as you go across the periodic table, whether you go up the periodic table or across the periodic table, of increasing electronegativity. Therefore, the least electronegative element that we'll consider is francium, and the most electronegative element is fluorine, because it's in the upper right but not a noble gas. The color coding you can see has some pattern to it here, that as you approach the fluorine corner of the periodic table, you have changing in properties, and that has a lot to do with electronegativity. So those color coding match up with the idea that the electronegativity increases as we work our way towards fluorine. So because we are going to mainly deal with the top three periods, the top three rows of the periodic table, I'll switch now to a view where we can see electrons for these elements. This graphic was just pulled off the internet somewhere, and they had said element number 1 was helium. It's clearly hydrogen, so I had to update it there. But otherwise, I think this is a fairly accurate periodic table. And this is showing the electron rings. The elements in the top row have 1 electron ring. The elements in the second row have 2 rings of electrons. The elements in the third row have 3 rings or shells of electron. And if we look at the outer electrons, all the elements here in this first group have 1 electron in their outer shell. Then we have 2 electrons in the outer shell. Another term for outer shell is the valence shell, valence electrons. These molecules here have 3 valence electrons, 4 valence electrons, 5, 6, 7, and then over at the noble gases we've got 8. With the exception of helium that can only hold 2 in its outer ring, of course. So we're going to ignore the noble gases. We're also going to ignore hydrogen for a second. If you remember hydrogen, or if you can remember, hydrogen here is colored yellow, which is kind of like these molecules over here. So it's going to behave quite differently than the other elements in its group as far as chemical bonds go. So ignoring hydrogen and ignoring these heliums, we're going to notice that these elements in the first row, first group, are very have a low electronegativity, which means that they are okay with losing an electron. So lithium would lose this electron right here, and sodium would lose that electron, with the idea being that if they lose their electron, the lithium would feel like it had a full outer shell of electrons like helium does, and if sodium loses that electron, it feels like it has a full outer shell and its outer shell would look a lot like neon. Meanwhile, while the elements here would lose an electron, the elements over here in the fluorine's column would want to gain one electron. If they could gain one electron somehow, the fluorine would look like neon and the chlorine would have a full outer shell just like argon. The charge, because you're gaining an electron, would be -1 for these elements here, fluorine and chlorine. These elements here, lithium and sodium, would lose an electron, so they would have one more proton than an electron, so they'd have a +1 charge. Meanwhile, beryllium and magnesium are examples of elements that could give up 2 electrons and have a total charge of +2. Now the story gets a little different as we move further towards the center of our periodic table, and that's because rather than completely losing or completely gaining an electron, there's some elements that would consider sharing an electron, so they're going to have covalent bonds. So let's take a look at a couple of elements that do those covalent bonds. One has carbon in the center, methane, and the other has oxygen in the center, which is water. H2O is water. Oxygen's awfully close to fluorine. Carbon's over here. We said the electronegativity increases as you go left to right. So we're going to look at what happens when you compare oxygen interacting with hydrogens versus carbons interacting with hydrogens. So in this molecule here, the methane, the electronegativity of the carbon and the hydrogens is roughly equal. Carbon does have a slightly more electronegativity than hydrogens, but they're pretty close to equal. Meanwhile, the difference between oxygen's electronegativity and hydrogen's electronegativity is fairly large. And what that means is that there's basically an equal sharing of electrons in these shared bonds shown here through the covalent bonds, and that there's no real strong area on this molecule that has a positive or negative charge to it, or a partial positive or partial negative. Even a partial positive or partial negative charge to it is pretty minimal. Meanwhile, oxygen is far more electronegative. That means it's greedy for electrons compared to those hydrogens, and so the electrons are going to spend the majority of their time hanging out around this oxygen rather than hanging around the proton that's the nucleus of those hydrogens. The smart podium at the auditorium sometimes makes my writing look weird as I save it in PowerPoint. But what this is meant to look like is that there's supposed to be arrows pointing from the hydrogen to the oxygen. Instead of just having a blue bar like shown over here, we've got an arrow. And then on the side closest to the hydrogen, we put a little cross bar there so that it looks like a little plus sign. This is an indication that because the arrow's pointing to the more electronegative molecule, you would have kind of a partial positive charge out here around the hydrogens and a partial negative charge around the oxygens, because it's partially positive, partially negative, depending on where you're contacting this water molecule. This molecule is considered to be polar. Instead of using those arrows with the plus signs, we could also use some symbols to represent where there's a partial negative charge. This is the Greek letter delta. Partial positive charge over here by these hydrogens. So rather than those arrows, this is an alternative way. So let's talk about what happens if you have a couple of water molecules interacting. We've got this first water molecule. It has the partial negative charges around this oxygen and partial positive charges around those hydrogens. A second water molecule moves into position, and we're going to get alignment between the partial positive charge here by this hydrogen and the partial negative charge here. And in fact, you even get a bit of a bond forming between those two, and that is called a hydrogen bond. The hydrogen bond is not as strong as these covalent bonds here, so it's a weaker bond than the covalent bonds, but it is a bond that if you add enough of them together, they do create a fairly, can amount to a fairly strong structure. And we'll get back to that with what happens when lots of hydrogen bonds form between water molecules. Here's a third water molecule moving into position and forming its hydrogen bond here with the partial positive charge on this hydrogen, that's an H, and then the partial negative charge on this oxygen. Okay, let's talk about what happens if you go from relatively few to relatively high numbers of hydrogen bonds between each of the oxygen molecules, or water molecules, excuse me. You can have gaseous water. You typically think of that as hot water, especially under 1 atmosphere of pressure. Under 1 atmosphere of pressure, liquid water would be okay to touch for the most part, and then solid water would be ice at normal atmospheric temperatures. And so in gaseous water, there's very few hydrogen bonds between the different water molecules because they have spread out. The whole reason a steam-powered engine works is that gaseous water takes up a lot more volume than liquid water. So typically you're thinking of things that are really hot when you get to this gaseous form. Meanwhile, liquid water, there's quite a few hydrogen bonds. They're forming and breaking fairly quickly, which gives water its fluid-like characteristic. And the water molecules can be packed in fairly densely. And then finally, when we get to solid water, this one has the most hydrogen bonds, and somewhat surprisingly, is that it's slightly less dense than liquid water. And the reason for that is that the hydrogen bonds have a specific distance they like to maintain, and if you have everything in a hydrogen bonds, they're basically spreading out from each other in a very regular pattern, whereas with liquid water, the water molecules are moving around and don't always maintain that spaced out pattern you see with ice. Moving on, now we talked about water-water interactions, but what if we put some ions in some water? So let's take a look here. We've got sodium and chloride. You might remember that that's table salt, and you should know that table salt will dissolve in water. Well, what does it mean that the salt is being dissolved? It means that this ionic bond that was between the sodium and the chloride was no match for these kinds of bonds, these hydrogen bonds that are kind of forming here, or pseudo-hydrogen bonds, I suppose, as the partial negative charge side of water molecules, the oxygen, all point towards the sodium molecule. And if the negatively charged region of the water molecules is pointed towards sodium, then if we think about it, if we had a negative ion like chlorine, we're going to have the water molecules arranged kind of in different ways, but in each of these ways you have a hydrogen, the hydrogen which is partially positive charge closest to the chlorine. So between all of these interactions of the water molecules interacting with the positive sodium ion and the negative chlorine ion, that's enough thermodynamic favorability that your salt will dissolve. There will be a point at which you keep adding salt to the water, you'll get to where the salt does not want to dissolve very easily, and that's because the water is already taken up by trying to arrange itself around the first dissolved sodium and chloride ions and can't necessarily take care of all the rest of the sodium and chloride ions. Okay, let's talk about one more situation where we have hydrocarbons, which are hydrophobic, hanging out in water. Hydrophobic means they fear water. So one thing that they're going to do is hydrocarbons, particularly things like lipids or long hydrocarbon chains, are going to form little oil droplets, basically. And as as you know, water and oil don't mix. So if we have a water molecule here, maybe it's oriented this way in relation to these zigzag lines are supposed to represent long hydrocarbon chains. So it's carbons with a bunch of hydrogens all around it. Bring in another water molecule, and this water molecule will interact with this other water molecule, and they're still essentially ignoring any sort of interaction with the hydrophobic material in this solution. And you can go ahead and continue to add water molecules around this lipid drop. And the water molecules, I got a little lazy here in how I'm drawing it, but the water molecules would completely form a wall around the lipid droplet, and so this would be like an oil-water immersion where you've got a little oil droplet that's suspended in water. As you know, with oil droplets suspended in water, like you shake up your oil and vinegar salad dressing, for example, it's somewhat emulsified to begin with, but over time the oils will float to the top because they're less dense than the vinegar, water, other solution in your salad dressing, and pretty soon the oil droplets will continue to form one giant aggregate, and you'll have separation of your oil and water. Now, hydrocarbons are nonpolar. We just went over that. However, you can put a functional group that is polar or charged at one end of the molecule, or in anywhere maybe. But here we've got an example where we have a carboxyl group, a carboxyl ion. It has given up its hydrogen, so it's got a negative charge here. And we've got the rest of the hydrocarbon tail, or acyl chain, if you will, showing that direction. Now that's here we're showing off, reminding ourselves that this part is hydrophobic. This part is hydrophilic because it was either polar or charged, depending on what the pH is. And because of that, this is a molecule that has a combination of both hydrophobic and hydrophilic regions. And so we call those molecules amphipathic or amphiphiles. I don't know if I'm saying that completely correctly, but that's the word you would use to describe molecules that have both properties. And here I've got a circle with a zigzag drawn off of it, which is supposed to be a shorthand version of this, where this circle at this one end represents a polar molecule, and then this is a bad bracket, but it was supposed to indicate that this zigzag tail, this hydrocarbon tail, is hydro, and that says hydrophilic, and it should say hydrophobic, so ignore that. So here, let me get rid of those. This is going to be shorthand for this molecule: hydrophilic, polar head, hydrophobic, hydrocarbon tail. So an example of where you might find a molecule like this is in soaps and detergents. So let's say you've got a bunch of water. The blue zigzags are our oil droplet hanging out in the water, and then you put in some soap and detergent, and those detergent molecules with the polar head and the hydrophobic tails are going to arrange themselves with the hydrophobic side pointing towards the oil droplet, and the hydrophilic polar end pointing away from that water droplet. And then you can continue drawing those molecules around here, and it continues all the way around this oil droplet. And at that point, you can see how soap ends up working. It works because it allows a oil droplet to move around and get washed away more easily in a water solution. This final chart is something we went over in the last lecture, but I'll go ahead and mention it again. We can go from having a trimer and a monomer, connect them together by pulling out a water molecule, and you can end up with a tetramer. This reaction can go in the other direction. You can have a tetramer go back towards this direction to be a trimer and a monomer, or maybe two dimers if it gets if it is broken in the middle of the molecule. So that brings us into this idea of going from monomers to dimers to oligomers to polymers. So we're going to, in the next few lectures, talk a lot about biological macromolecules. Our four categories of biological macromolecules are nucleic acids, proteins. I say polysaccharides here, but I switched to referring to them as carbohydrates soon. And when we get to that lecture, I'll explain that. And then lipids. Polysaccharides is an okay term if you're talking about macromolecules, but monosaccharides are fairly common and are relevant, just to give you a preview. So for nucleic acids, we've got nucleotides that are used for making DNA, which are A, T, C, and G, and we have nucleotides used to make RNA, which are A, U, C, and G. In addition to the T and U difference, we are going to talk about a slight difference in the sugar part of the nucleotide molecule. That'll be in the next lecture. If you have two nucleotides together, it's a dinucleotide. This is sometimes used by bacteria or other molecules as signaling molecules, so these dinucleotides are relevant to a lot of the biology we might get into. Meanwhile, you have oligonucleotides, which will come into play, for example, when we're talking about DNA replication. And then polymers, we've got nucleic acids, DNA and RNA are the two types of nucleic acids. Next up, we have proteins. Monomers that are used to build proteins are amino acids, and there are about 20 of those. So where we only had 4 to choose from for DNA and 4 to choose from for RNA, we've got 20 to choose from for amino acids. Dipeptides, diamino acids are not too relevant about anything that we're going to talk about in the future. Usually you continue extending your amino acid chain until you have either a peptide or a full-out protein. Next up will be polysaccharides, monosaccharides. We'll talk about 3 kinds of monosaccharides. Disaccharides, we'll also talk about 3 kinds of those. Oligosaccharides, there's a few that we'll get into. And then finally polysaccharides. There's quite a few polysaccharides that have important biological functions, and later on we will give examples of some that you might find in plants or in animals, and the polysaccharides that are used for different purposes. So that'll be in a couple lectures. And finally, lipids. Lipids are kind of monomers anyway. They can form groups or clusters, but these aren't held together by covalent bonds, so I'm saying it's not really a polymer. Usually, if they're together in a big cluster, it's because they're trying to get away from water, because they are hydrophobic. So anyway, that is a preview. The next 3 or 4 lectures we'll cover these different biological macromolecules in far more detail. Alright, talk to you later.